Since the dawn of time, mankind has always held a fascination with space. In ancient times, people would use the stars of the night sky for several different purposes. Some stars were grouped into pictures and used in storytelling. These are now known as constellations to us today. Other stars, such as the North Star, were essential to nighttime navigation in a time before accurate maps and satellite GPS. However, space was always a distant entity. The pictures of mankind were always so distant, and there was no way of seeing them close up. That was until 1609. According to NASA's historical records, that's when Galileo Galilei, an Italian mathematician, engineer, physicist, and astronomer, developed the first telescope. Now, this telescope wasn't of much help. It made the stars slightly larger, and they still appeared blurry, but it was a first step in a 400-year-long process of developing technology to be able to see deeper into outer space. Today, modern telescopes have reflecting mirrors and lenses as large as 1 meter, 2 meters, even 5 meters wide. One of the leading types of modern telescopes is the Schmidt Cassegrain telescope system. This system combines a unique mounting and reflective optics system to create one of the best amateur telescopes on the market. The thing about the standard tripod is that it allows the telescope to move in one of 4 standard directions: up, down, left, or right. Now, this is a great coordinate system, and it's what we as humans are used to thinking in. It's the way we're raised to think of coordinates in elementary school math. The problem is it doesn't translate to space very well. The thing about stars is that they tend to track across the night sky in arcs, which means if we move telescopes up, down, left, and right, we have to constantly adjust them to keep track of the star. The thing about the Schmidt-Cassegrain system is that it uses what's called an equatorial mount. This means that the telescope is mounted such that its 0 point is aligned with the celestial equator of space. What that means is here on the telescope behind me, you can see that it's at an angle. It's not sitting in the standard plane that we're used to. That's because this telescope is celestially aligned. This angle here is 41 degrees, and that's approximately equal to the altitude of us here in Lincoln. Lincoln's located about 41 degrees north latitude. From here, the telescope can then rotate in 2 new dimensions. The first, up and down, is what we call declination. That's like moving up and down on the latitude scale of Earth. Or similarly, it's like how airplanes will pitch their nose up or down. The telescope can also move in another direction, which is similar to moving along the longitude lines of Earth. So this will allow it to rotate left or rotate right. This new coordinate system makes it much easier for the telescope to track objects through the night sky. Now, in combination with the equatorial mount system, something that makes the Schmidt-Cassegrain telescope system unique is its catadioptic optics system. In a typical telescope that you may be used to from growing up, the light will come in from the front here, travel down to the back, reflect off a mirror, reflect off a second mirror, and be projected out an eyepiece on the side. In a Schmidt-Cassegrain, that second mirror redeflects the light towards the base of the primary mirror. So in this case, we see the light comes in here, it will reflect off a mirror back here, there is a second focusing mirror right here, and then finally, the eyepiece is located right here. The advantage to this system is that you don't get the distortion that you generally get with a Newtonian optics system. By deflecting the light out to the side, the Newtonian optics tends to distort the image in one direction or another. With a Schmidt-Cassegrain, you remove this distortion. Something else unique about the catadioptric system is that it combines lenses and mirrors. Most telescopes use either mirrors or lenses exclusively. The Schmidt Cassegrain uses a combination of these lenses and mirrors to preserve the highest quality of light possible. Now, you can buy any sort of telescope out on the modern market. Schmidt Cassegrains, Newtonians, you can buy tripod mounts, equatorial mounts. The thing that's great about the Schmidt Cassegrain is that it's a great all-around telescope. Most telescope systems, you may be wondering, why does it matter about the mounting system or the reflective optics? A telescope's a telescope, right? It looks deep into space. Well, the Schmidt Cassegrain holds several advantages over several of its competitors. According to Telescopes.com Telescope Buyer's Guide, the Schmidt Cassegrain is phenomenal for deep space observation as well as astrophotography. Let me show you why. Here in this diagram, you can see the two coordinate systems that we discussed earlier. This one on the left here is the Cartesian coordinate system. That's the way we generally think as humans. This one on the right is the way that a Schmidt Cassegrain moves. Over here, we can say, a star starts here. This is where you start observing a star at the beginning of your night. Over the night, that star is going to move up to here. If you're using a standard tripod mount, you have to move in two directions in order to track that star. You have to move left or right, and you have to move up as well. Now, that's very complicated, especially when it comes to astrophotography. The thing about astrophotography is that you're generally taking very long exposure shots, and so you want as minimal movement as possible. That is one key advantage the Schmidt Cassegrain holds. In this instance, the star will start right here at the night. So this is where we start taking our pictures. As the night goes on, the star tracks along this arc right here. Now, because this telescope system is designed to move in that arc, you don't have to move it up or down. You only have to move the telescope in one dimension. That's a huge advantage for anybody taking any sort of photographic shots of space, especially very long exposure shots. If you start moving things in multiple dimensions, you're more likely to lose the precise track of the star, and images will come out blurry. One other great thing about the Schmidt Cassegrain system is that it packs the power of a telescope 5 times its size into a smaller package. The way the optic system works, it essentially multiplies the focal length of the mirrors and the lenses within the body of the telescope by a factor of 5. This allows for much greater field of view shots, and you can see much better pictures of space with a much smaller design. In order to get the same focal length power out of a Newtonian telescope with a tripod, something called a Dobsonian telescope, you would need something 5 times the length of this here. One additional factor that makes the Schmidt Cassegrain such an amazing telescope is that it pairs very well with computer software. There's a lot of software out on the market today for tracking stars and finding celestial objects that may not be as common to the common person. People that go out and observe astronomy all the time may know where to find Aldebaran or Albireo, but the common person may not. These computer software systems make it easy to find those types of objects and can present you with absolutely amazing views of celestial objects. These work really, really well with Schmidt Cassegrain systems, again, because of the way the telescope is designed to move through space with the star, as opposed to thinking in the standard Cartesian plane. Now, due to its advanced optics system and mounting system, the Schmidt Cassegrain is one of the finest telescope systems on the market. Despite it being a little pricier than a standard Dobsonian telescope, it's very much worth the investment. Had Galileo had access to a Schmidt Cassegrain system, 400 years ago when he first invented the telescope, he would have been absolutely blown away. Thanks for watching.